Hello, welcome to the DAS session. So in this session, I'm going to explain the dividing master method for the recurrence relation. So especially dividing master method is used for the dividing recurrence functions. It is used to calculate the analyzing time for a particular function. So we're gonna calculate the solutions for these functions in big O notation. So for now, the dividing master method general uh, like the general appearance, the general formula for the dividing master function is T of n is equals to a T of n by b plus f of n. Given that we have to assume here a is greater than or equal to 1, b greater than 1, and also here f of n is written as big O of n to the power k log n to the power p. So this is how we write it, and we have three cases in which we get the solution. So these three cases are divided depending on the relation between log a to the base b and k. So depending on the relation between these two, we have got three cases, and each case has different general solution. So the first case is log a base b greater than k. So when log a base b greater than k, we have the general solution as big O of n to the power log a base b. This is case 1. And when log a to the base b is equals to k, then we have three more cases in which we're gonna depend on p, and those three cases are p greater than -1, p equal to -1, and p less than -1. When p greater than -1, the general solution is gonna be big O of nk into log of n to the power p plus 1. When p is equals to -1, the general solution is gonna be big O of n to the power k into log n. When p is less than -1, the general solution is big O of n to the power k. When it is in the place of big O, you can also take big theta, which gonna tell the average case solution for the algorithm we are taking, and this is all case 2, and there is another case which is case 3. In here we're gonna the case is depend on the situation that log a base b is less than k. Then you again gonna depend on p, where p greater than or equal to 0, you have the solution as k, big O of n to the power k into log n to the power p, and when p less than 0, the solution is big O of n power k. So this is how the recurrence relations are solved. The recurrence functions are solved using the dividing master method, and whatever the solution we are getting, it's gonna be the analyzing time for that particular algorithm. And so I'm gonna take example to understand this dividing master method more. So let's take T of n is equals to 8 into T of n by 2 plus log n, where a is equals to 8, b is equals to 2, and we don't have the n term here, so k gonna be 0, and p is equals to 1. So let's calculate log a to the base b, that is log 8 to the base 2, which is gonna be 3, and we got k as 0, so absolute. Therefore log a to the base b is greater than k. So this is case 1, and we're gonna have the general solution as f of n is equals to big O of n to the power log a base b, which is n cube. So the solution for the recurrent relation that I have taken is big O of n power 3. So the analyzing term for this recurrence relation is big O of n cube. So this is why master method is used to calculate the analyzing time for the recurrence solutions. For normal algorithms, we can calculate the like analyzing time by like using limits and different processes, but for the recurrence relations we use master method to calculate the analyzing time in asymptotic form. And I'm gonna take another example. Let's see, we can get it in a different case. So let's take T of n is equals to 16 Tn by 2 plus n cube, or let's take n power 4 log n. So here a is equals to 16, b is equals to 2, k is gonna be 4, and p is equals to 1. So let's calculate log a base b, which is log 16 to the base 4, base 2, which is gonna be 4, and k is equals to 4 too. So in this case we got log a base b is equals to k. So now we're gonna depend on p. Here we have got p is equals to 1. So which is p greater than minus 1. So in this case our general solution is gonna be big O of n to the power k log n to the power p plus 1. That is big O of n power 4 log square n. So this is our analyzing time for the recurrence relation I have taken. So this is how the recurrence relations are solved. So let's do like one more example, which will be in case 3. So let's take T of n is equals to 8 log, cancel this. T of n is equals to 8 T of n by 2. So as you know, we're gonna get a value, so we're gonna get the log a to the base b value as 3. So I'm gonna take a more greater value than this value in the next. So it's gonna be n power 4 log square n. So as you know, here we're gonna get log b to the base a as 3. We got k equal to 4 and p is equals to 2. So as you see here, it is log a base b. Log a base b is less than k. So it is in third case, and now we have to depend on p. We have got two cases as p greater than or equal to 0 and p less than 0. As we have p equal to 2, so we're gonna get this case, and the general solution for that case is big O of n power k log pn, which is gonna be big O of n power 4 log n square. So this is the solution for the recurrence relation we have taken. So we have seen 3 cases. So depending on these 3 cases, the entire solution of the recurrence relation is gonna depend on a value, b value, and k value, and p value. So when you do the recurring trees for the recurrent solutions, you gonna understand why we are taking these a, b, and k values. So as we know, the b value is the depth of the tree, and that is how the recurring trees goes though. So I think you will understand, if you study more about the master method, we will understand why we are taking a, b, k, and p values, and why the solution of this recurrence relation is depending on those values. So This is how the master method is, especially the dividing master method is used for the to calculate the analyzing time for the recurrent solutions. As this, we also have the linear master method, which will be used for linear recurring solutions or linear recurrent functions. So that's it for today. Thank you.